Hi guys, Mrs. Aldivia here, and today we're going to be talking about acids and bases. This is chapter 12 of our Rebel textbook. So, to introduce acids and bases are everywhere, right? We use them all the time, and sometimes we don't even know it. Um, so, common household items that contain acids can be like our citrus fruit, the vinegar, which is an organic acid, all of these citrus fruit, citric acid, organic acid. We also have like hydrochloric acid or maloric acid that we use in cleaning our swimming pools, or sulfuric acid that we use inside of soda. We can also look at bases. Now, remember, acids are compounds that have a pH below 7, 7 being our normal pH. And bases are pHs that are substances that have a pH greater than 7. So, Drano, the stuff that we use to clean our sinks when they're clogged, baking soda, those are all bases. Same thing with like the soap that we wash our skin with, is also a base. All right. So there's two ways to define an acid and a base. There is the Arrhenius definition and there's the Bronsted-Lowry definition. So we're going to look first at the Arrhenius definition and then we'll look at the Bronsted-Lowry. So for in acids are compounds that produce hydrogen ions in water. So they're producing the hydrogen ion in the water. Okay. So an example, if we have HA, A stands for acid, that is going to dissociate and give us hydrogen ions and whatever it is that was combined with that. So it could be chlorine, it could be sulfur, it could be nitrogen, bromine, iodine. Any one of those compounds would produce an acid. If we recall, an acid basically has the hydrogen in front of it, and that's how we identify that we have an acid. The example that they used here was with hydrochloric. So let's go ahead and write this example down. So we have hydrochloric acid. Let's do it right here. HCl, and this is aqueous. And that's going to produce the hydrogen ion plus the chlorine ion. Now, chlorine has a full octet because it stole the electron from that hydrogen that it was attached to. Okay. Now, there's another way that we could actually see this acid. Okay, so this is the first way right here. And the other way that we could actually demonstrate this acid is going to be demonstrating it with water. So if I have HA plus H2O, I'm going to produce H3O ion plus the A ion, all aqueous. The only difference is that this one does not show the water and this one shows the water. They're the exact same reaction, and we're going to show that using the hydrochloric example that we just did. So hydrogen chloride, aqueous, plus water, H2O, is going to produce H3O plus our chlorine ion. And they're all aqueous. No, except for water, which is a liquid. Water is a liquid. Okay. So one more time, this one without water and this one with water. So let's write that down so that we don't forget. So this one is showing the dissociation without water, and this one's showing the dissociation with water. So it's good to know that difference and see the differences. Now let's go ahead and name these two that we just produced, these two ions. So the first ion that we saw was quite simple. This is just our hydrogen ion. And the next ion we saw, the H3O, that is going to be the hydronium ion. That is a really cool word. I like saying it. It sounds like a flower. Hydronium. Hydronium. ion. And that basically is the dissociation with water, and then the hydrogen ion is the dissociation without water. Remember, all reactions are occurring in water. That's why the definition says compound produces hydrogen ions in water. The difference is we show it with and we show it without. Why? This is a lot simpler to balance and write down the equation. We don't get lost with all the oxygens flowing around everywhere. And this one, we can get a little bit lost sometimes showing that reaction. We already know it has water, so you pick your poison on that one, but make sure that you solve it as your question asks for it to be solved. All right, so now that we've done that part of the acid, quickly on the base. So a base produces hydroxide ions, OH. Hydroxide ions inside of water. Okay. These hydroxide ions, you'll notice that you have MOH, and that's going to give us M plus OH. The M stands for a metal, so that's going to be our metal ion. Now I'm going to write this down in a little bit, not quite yet, because there's something else I want to write about my acids before I go into that base. So we'll come back to the base. This is just showing the dissociation of hydrochloric acid inside of water. You can see that the hydrogens attracted to the oxygens, right, spreading through. So this is creating a hydrogen bond, right? Hydrogen bonds are very strong. We learned that through our chapter 5 of covalent compounds. And then the chlorine anion, the hydrogens from the water are being attracted to the chlorine ion. And that's our dissociation. And this is the example we just gave here, showing the dissociation with water. So showing it with water. And you can see it's same reaction. All right, so the two ways to show it, we just covered that. Now it wants us to show nitric acid ionizing in water. We have a little bit of space. We could actually write that one down in our tiny space here that we left. Let me get a different color. All right, this one's a nice color. So if we're going to show nitric acid dissociating, water not included, that's going to be this one right here. So the example is going to be HNO3, and this is going to dissociate. It's aqueous. Remember, donates hydrogens. So the hydrogen is going to leave. So we get the hydrogen ion plus the nitric ion. And these are all aqueous. Okay. See how we did here? Perfect. And then we want to show it with water. So if we show it with water, now we're going to include that H2O. So we're going to have HNO3 aqueous plus H2O liquid. And that's going to give me H3O positive, and this is aqueous, plus the NO3 ion, which is also aqueous. All right, let's see. Perfect. All right, so you guys, as you can see, those ones are really, really simple to do, right? Easy peasy. Okay, so this is the other part I wanted to actually add about our acids. It's going to be polyprotic acids. So polyprotic acids are basically acids that produce more than one hydrogen ion in our reaction. Fix the camera here so we can see with the paper. All right. So let's go over polyprotic acids. Polyprotic acids. Okay. So polyprotic acid releases more than one hydrogen ion. Okay, it's going to release more than one hydrogen ion. So what are polyprotic acids? Sulfuric acid is a polyprotic acid. So you'll notice that sulfuric acid is H2SO4. That means it has two hydrogens available to donate. So we have different types of ionization. First ionization and second ionization. So in first ionization, we're going to be losing that first hydrogen ion. And when that happens, you're going to have one hydrogen leave, and you end up with HSO4. That's your first ionization. The second ionization then happens, and you have HSO4, and that hydrogen is going to leave, and it shows like this, the hydrogen ion on its own, and then you just end up with SO4, that sulfate ion. No longer do you have hydrosulfuric acid, which is this one here. So you see two steps, first ionization and second ionization. So you will have a first ionization. So that is when you lose your first hydrogen ion. And actually, let's write it down. So we have H2SO4, right? And we know this is occurring in water, so I'm not going to write it down with the water. You get your first hydrogen leaves, and you end up with HSO4. Then the second ionization happens. So this is first ionization, and then the second ionization is going to occur. And we're starting off with this one, the product that we left off with. So the product that we left off with, HSO4, is going to then dissociate, and we're going to have that hydrogen ion. So that's hydrogen ion number 2 plus SO4 negative. Okay. So polyprotic, basically, you're just losing more than one hydrogen ion. Monoprotic, or just call it protic, right? Meaning our proton. So they release one proton, and that's your hydrogen ion. Actually, let's write that down here. That hydrogen ion, that also represents our proton. So this is also our proton. A hydrogen ion. Diprotic means you're releasing 2, and then you have triprotic, which means you're releasing 3. As you can see, phosphoric acid is a triprotic. There is more than one. However, these are just the examples that we're using. So if you see H3, you know you're going to have a third ionization occurring. These were just examples of how you release them, and you would just repeat that process depending on how many hydrogens you have attached to that acid. All right, so that was the Arrhenius definition of our acid, and I want to now go back and write the one down for our base. Okay, so the base maybe I should write, you know what? No, this is fine. The base is quite simple. As you can see, most of that first part of the PowerPoint basically just talked about the acid. So the base is going to be written like this for our example. MOH, aqueous, produces your metal ion plus a hydroxide ion. So the base produces hydroxide ions in water. So the example was KOH, potassium hydroxide, aqueous, gives me potassium metal plus my hydroxide ion. Right? And I don't seem to have too much space left here, so I'm just going to write it on this end. OH with the little negative sign on the top is equal to hydroxide ion. All right, so that way you guys can see that. That's a hydroxide ion. And that's a little section that we have for our base. Done with the base. All right, let's now go into the Bronsted-Lowry definition. Okay, so the Bronsted-Lowry definition is different. It doesn't produce hydrogen ions. It donates hydrogen ions. So this definition is a bit different in that acids donate hydrogen ions inside of the reaction, right? And bases accept hydrogen ions inside of the reaction. So compound donates hydrogen ions if it's an acid, and it accepts hydrogen ions if it's a base. So I'm going to write acid here, even though I know I have it here, but okay. So in the acid, you're going to see the example. These kind of work together here. So the same example of the hydrochloric acid producing that hydronium ion. Okay. You could clearly see that this one accepted, and we could clearly see that this one got donated. So that hydrogen got donated, right? So therefore, this is my acid. And I know this because chlorine is all by itself. This one accepted, right? So this one, therefore, must be my base. Okay. So we donated hydrogen ion, and this one accepted the hydrogen ion. The H2O was, well, actually, the H2O accepted it. So actually, I should write that. This one accepted it. Right? And this is where it landed. We could see that it landed here. So, and then we end up with anion by itself. All right, so acids donate, bases accept. Okay. The other example they had was the H3N, and we can see that even though they both have hydrogens in front of them and they're both acids per se, the hydrogen from the chlorine is the one that leads, and the base accepts it. Okay, so this is actually our ammonium, right? So NH3 accepts, we could see that right here. It is now NH4. That makes this one a base and that one an acid. So you have to know what you're producing in order to be able to tell if you have an acid or a base based on the Bronsted-Lowry definition. So let's write this down kind of like it's showing us so we could remember how the hydrogens are moving inside of our reaction. Here is my water plus my hydrochloric acid. In this reaction, we could see that these electron pairs are being attracted, or they're attracting this hydrogen. So actually, I'm going to move it like this instead, because the hydrogen gets attracted to those electron pairs. These electron pairs go to that chlorine. Now, chlorine already has 7 valence electrons, right? This now produces our hydronium ion, and our hydronium ion has a positive charge, okay, right there, because these electrons that it normally had, oxygen normally had these free electrons, right? That second pair is now being shared with that hydrogen, plus our anion right there. Okay. So you could see that the water acted as a base, and the hydrochloric acid reacted like an acid because it donated. Right, that was the other example that we could see right here. Same process, donation of the hydrogen ion to our base, creating this NH4 and this anion right there. Acid, base. Now, there's something else we're going to talk about with acids and base, and that is that we're going to have something called conjugate acids and conjugate bases. Okay, so recap really quick. Acids donate hydrogen ions, and bases accept hydrogen ions, right? Now, water can behave as both an acid or a base. Let's actually write that down. Water can be both an acid and a base. Okay, so water can break and give you an acid and a base. Okay. Let's actually go through a quick little example of how a water breaks apart to give you that acid and that base. So we have H2O, water, plus H2O. Well, the dissociation is going to happen and we are going to end up with H3O, right? So you're going to have a hydrogen leave plus OH. Quite simple, right? One of these hydrogens from that water went to the other water, creating H3O. So now we had an acid here because it donated that hydrogen, and a base here because it accepted that hydrogen. Okay. Now, like I said, the next thing that I wanted to talk to you guys about is going to be conjugate acid and conjugate base, right? And I want to know, what is the definition of our conjugate acid and a conjugate base? It's quite simple, right? We'll go back to this part right here. Okay, so a conjugate acid or a conjugate base is basically the molecule or the compound that accepts the hydrogen is now considered a conjugate acid. Okay, so this is now my conjugate. Let me make sure I spell this right. Conjugate. Conjugate acid. And this one's my conjugate base. Conjugate base. Okay, how is that even possible? Well, that means that if we reverse the reaction, if we were to reverse this reaction, this behaves as a base and this one's going to behave as an acid. This will donate the hydrogen to my base, creating this same product all over again. Okay, so that means that this reaction could actually go both ways. Okay. This reaction could go both ways. There's a name to this principle that I hope pops up on the PowerPoint because I can't remember the name of it right now. So stuff like a Le Chatelet's principle, in which the reaction has an equilibrium base going back and forth with each other, right? So it's like Le Chatelet's principle. Okay. All right, so let's look at this example right here for this organic acid. So in this acid right here, you see that it donated that hydrogen ion. So now the part that donated is called your conjugate base. The base, which is the one that accepts the hydrogen, we could tell that accepted has one more, is now your conjugate acid. This is an acid-base pair. Okay, acid-base pairs. So let's write our acid-base pairs down. Okay, so this one is going to combine with our conjugate base right here. And that's going to create an acid-base pair. And the same is going to happen with these ones right here. This is also going to be our acid-base pair. All right, I'm going to put little ditto marks on that one. Okay. So as you can see, conjugate acid, conjugate base is basically the same thing. This example showing it with the dogs. All right, here's a little funny moment. Here's a dog on acid, and the dog donates its acid to the cat, right? And so now you have a conjugate base dog. He's now basic, and the cat has the hydrogen, so now the cat's on acid, right? Little funny moment, but then if the cat gives the acid to the dog, then that dog becomes that acidic dog. All right. So a conjugate base is identical to the acid, but without the hydrogen ions. All right. The next example that we're going to talk about that you're going to see here, some of you guys might recognize this. I hope not. I hope if you do recognize this, you're only recognizing it because you've learned about it in a biology class and nothing else. So the first one we have here is a picture of cocaine, right? And cocaine is actually an acidic product, right? And in its more pure form, it's an acidic product, right? This part right here, this powder form, more expensive than this part here. This is called crack cocaine. So this one's crack cocaine, and this one is regular powder cocaine, right? The one they call snow or something. So regular cocaine, you could see this salt right here. If you guys pay attention, you could see that the hydrogen ion is attracted to that nitrogen, right here. And the chlorine is kind of gone, right? And this is because they washed it in hydrochloric acid, right? That's why it creates holes inside of your nose if you snort it, right? So do not do cocaine. Drugs are bad for you, right? Crack cocaine now is when they baked it with some baking soda. Right? So they took some baking soda and then they bake it and they harden it, right? One, it creates more impurities inside of it, so it creates more, and it's easier for them to transport this solid form than it is for them to transport the powder form. So this is now considered a base. Okay, crack cocaine is what can I say? It's so harmful for your body. You could see a lot of people. You could tell when someone's using crack cocaine. Very addicted. You like kind of sad, but if you think about the people that are on crack cocaine versus normal cocaine is usually like the super powerful like movie stars and stuff. You can't really tell they're on something. And then crack cocaine, you could see it all over their body that they're on it, right? Either way, don't do drugs. Okay. All right. So this one says, identify the acid-base pairs in the following equilibrium reaction. Let's go ahead and see if we could do this together. Hydrobromic plus CH4O. The CH product, so this hydrocarbon, picked up a hydrogen ion. Therefore, this is an acid, and this is my conjugate base. This is my acid. This is a base. This is my acid. This is my conjugate base. This is an acid-base pair. These two right here. My base picked up, right? It picked up that hydrogen. So this is a base. And this one right here is my conjugate acid. All right. Oops. I said those wrong, didn't I? All right. Acid, base. Donates and accepts. So the acid turns into a conjugate base, and I said conjugate acid earlier, right? And this base right here, now it's going to be my conjugate acid. It's still, these are my acid-base pairs, and actually, no, this is my acid-base pairs. Oh my goodness, I totally messed that one up. Whew, this is why we write things down, which is what I am exactly going to do right here before I make things worse for myself. I'm here still thinking about why we shouldn't teach the cocaine lecture here, and my brain forgets what I'm doing. Okay, now that I could see these, I'm going to write them down. This is my acid. It has that hydrogen right there. That hydrogen now went here. This one's going to be my base. Right there. The one that accepts, right, the hydrogen, it now becomes my conjugate acid. So I'm going to write Ca for conjugate acid. This one now becomes my conjugate base. Because if we were to flip it over, this one here is going to accept that hydrogen ion. So it's going to behave as a base if you go reverse. And let's go ahead and rewrite it in the reverse format just so we could see that. So bromine plus CH5O is going to produce the hydrobromic plus CH4O. Now that it's in reverse, we could see that here is that hydrogen and it's going to go here. So this is going to be my base and this is going to be my acid because it's in the reverse format. Right? And remember, the reaction goes both ways. All right, much better when we write everything out, okay? Right. Now, on one section, we were talking about weak acids and weak bases. So I'm going to go back up on that PowerPoint just so we could reference the weaks and strongs and whatnot. Okay. So in acid-base equilibrium reactions, this is what we were seeing right here, this equilibrium, okay? And Le Chatelet's principle, which talks about equilibrium. Okay, let's write that word down. It's actually a nice word. So it's equilibrium reaction. That double arrow, that's an equilibrium reaction. So strong acids completely ionize in our water, completely ionize, break apart and whatnot, while weak acids only partially ionize inside of water. Hydrofluoric acid is considered a weak acid and only partially ionizing. But why is hydrofluoric acid a weak acid versus a strong acid? Well, that has to do with fluorine being the most electronegative element, and it wants to keep its hydrogen with it, wants to keep it connected together. So in a weak acid, right, this right here is going to be attracted. So you're going to have more of this and less of your product, okay? More of your reactant, less of your product in a weak acid. Even though the reaction goes both ways, you notice that it's not always equal as the word equilibrium suggests. Equilibrium is only saying that the reaction goes in both directions. The rate in which the reaction occurs actually differs. Okay, it's not an equal rate. Okay, so this all depends whether you have something strong or something weak. And if it's weak, we have to figure out what the rate of the reaction actually is. So I think we're going to be talking more about rate of reactions either later in this chapter or it's going to be chapter 13 where we talk about rate of reactions. Okay. Now we're going to skip this because we already talked about it. All right. So conjugates of weak acids are basic and conjugates of weak bases are acids. So that's what we were just talking about here. Okay. Conjugates of weak bases are acids and whatnot. Acidic, basic. How do we know? Hydrogen ion on this one, no hydrogen ion on the other one. Quite simple. Just look for the hydrogens. Which one has more? Which one has less? And that should actually let you know what you have. All right. So this next section is reactions involving acids and bases, where we're going to talk about acid-base neutralization, acids with metals, and formation of acids from non-metal oxides. This is going to be in the next video, part 2. Ciao.